UNSW NV15 dataset with TeamDoomsday. The overview: the raw network packets of the UNSW NV15 dataset were created by the IXIA Perfect Storm tool in the Cyber Range Lab of the Australian Centre for Cybersecurity for generating a hybrid of real modern normal activities and synthetic contemporary attack behaviors. The dataset is a network traffic dataset that contains network traffic data captured in a research environment. The dataset has a total of 2,540,044 records, which are divided into training and testing subsets. The TCP dump tool is utilized to capture 100 gigabytes of the raw traffic. This dataset has 9 types of attacks: fuzzers, analysis, backdoors, denial of service, exploits, generic reconnaissance, shellcode, and worms. The Argus and Bro IDS tools are used, and 12 algorithms are developed to generate a total of 49 features with the class label. The dataset is divided into training 80% and testing 20% subsets. So first, we clean the data by removing duplicate and irrelevant data points and any incomplete or null values. Then we chose the most relevant features and removing any irrelevant ones in the intrusion detection dataset. For feature extraction, we were removing unnecessary or highly correlated features, encoding categorical features, and feature scaling, where the steps performed during feature extraction. By removing unnecessary features and highly correlated features, encoding categorical variables, and scaling the features, we have prepared the data for the machine learning model. These steps help to reduce the complexity of the data and ensure that the model can learn from the most important features of the dataset. So for feature scaling, the algorithms used are decision trees, random forest, and k-nearest neighbors. Decision trees do not require scaling because they make decisions based on the relative values of the features rather than their absolute values. Random forests are like decision trees, but they do not require scaling because they are made up of multiple decision trees that make decisions based on relative feature values. And KNN performs best when the features are scaled to similar ranges, such as the z-score normalization or min-max scaling. Feature scaling helps to normalize the range of features, making the distance metric more fair and accurate.
Coming to algorithms, to develop the intrusion detection system, here we have used three algorithms. Those are like decision trees, random forest, and k-nearest neighbors. These are all popular machine learning algorithms that can be used for classification problems, such as detecting whether the network traffic is malicious. Coming to the decision tree algorithms, it creates a tree-like model that partitions the dataset into a smaller subset based on the values of the different features, ultimately leading to a predictions for each data point. And the popular algorithm, due to its simplicity, interpretability, as it allows us to understand which features are most important in making predictions. Decision trees are usually, they are prone to overfitting, and if the tree is too deep or it is, there are too many features. Coming to random forest, it is an extension of a decision trees that uses multiple trees to improve the accuracy of a model and reduce the overfitting issues. By creating many decision trees on random subsets of the data, the model is able to capture more complex relationship between the features and the target variable. Random forests are often more accurate than a single decision tree, and they are less prone to overfitting, making them a popular choice for many classification tasks. So coming to KNN, which is K nearest neighbors, is a machine learning algorithm which is also a popular method that can be used for both classification and regression problems. It is non-parametric algorithm that makes no assumptions about the underlying distribution of the data. The basic idea behind the KNN is to find the K closest data points to new unseen data point and use the majority class of these neighbors to make a prediction. Here, the choice of the K is a hyperparameter that can be tuned to optimize the model performance. Can handle non-linear decision boundaries and it adapt well in changes in underlying data distribution. It is computationally very expensive when the size of training set is large, and it is very sensitive to the choice of distance metric and the scaling of the features. And here we can use cross validation to estimate the generalization performance of the model. Hence, Kanan can be also useful algorithm for wide range of applications, including such as like image classification, test classification, and recommendation of systems also.
So coming to the part of model training and testing, we have basically split the data into testing and training sets. And as we mentioned before, the training set consists 80% of the data and the testing contains 20%. We have trained three different models, that is the decision tree, the random forest, and the KNN. Um, so the decision tree basically does classification in the following way. It just breaks down a data set into smaller and smaller subsets, while at the same time, an associated decision tree is incremented. That is how the decision tree works. And the random forest is used similarly. It just uses bagging and feature randomness when building each individual decision trees to predict whichever category it belongs to. After that, we have made use of the k nearest neighbors. What it essentially does is it just tries to find the nearest neighboring point that belongs to a particular category and tries to um, go around its classification process. Yeah, this is basically the data distribution of the training and testing sets. As you can see how it is distributed, the normal and the attack is almost it's equal in the training set. However, there is a huge difference in the testing data set. Um, the number of points in the length of the training set is 82332 and the test set is 175341. Coming to the part of how we have carried out the evaluation, we have basically carried out the evaluation in the form of accuracies and confusion matrix. The confusion matrix is essentially a table that summarizes the performance of classification by comparing the predicted labels to the actual labels of the test set. The table has four cells. That is the true positive, the false positive, the false negative, and true negative. In the accuracy section, the decision trees, the random forests, and the KNN all have performed very well. However, we can see that random forest has performed well on the testing set with 95% accuracy.
So some another forms of evaluation we used precision, recall, and F1 score. So precision generally measures the accuracy of the positive predictions, while recall measures the completeness of positive predictions. In precision, we consider all the positive samples that are correctly classified or not. And in recall, we mostly care about correctly classifying all the positive samples. F1 score is also a good metric for evaluation. It is generally the harmonic mean of precision and recall. F1 score is it's like the weighted average of precision recall. So F1 score it considers the true positive, true negative, false positive, false negative, the combination of precision and recall, and it is mostly useful. It is more useful than accuracy if we have an uneven class distribution. So for decision tree, we got around zero point 0.9, so which is like a good score for evaluation. Moving on to random forest. Random forest was the best one we got. Again, it's a little more than the decision tree. It's close to 0.95, and KNN we that was the third one. Can you move on to the next slide, please? Yeah, so we got a slightly lower score for KNN, but it's still like a good score around 0 0.9, 0.85, 0.95. So the average is close to 0.90. The accuracy is 0.91. And moving on to the next slide, we performed visualization using PCA. So as the data set had like more than 16, 17 features, so for better visualization purposes, PCA is a good algorithm. So PCA is used in dimensional reduction techniques to reduce the number of features, and it helps in retaining most of the information. So basically used to visualize high dimensional data by projecting it onto a lower dimensional, and it also preserve the information as much as possible. So in our case, we first applied PCI to dataset to reduce the number of features and then plot the data points into 17 types like PCA1 to PCA17. And finally, we plotted the PCA1 and PCA2 against each other for some better visualization purposes. And moving on to conclusion now, we can conclude that the like decision tree, as you saw, it had better accuracy scores compared to KNN. And out of these two, again, random forest was slightly better, having 0.02 higher accuracy. So you can conclude like random forest performed the best for intrusion detection for the US NW dataset. Yep. Thank you.